Dear ladies and gentlemen, welcome to this video. Today we will explore different autopilot systems for drones. The video is structured into two parts. The first part is theoretical, where I will explain the main concepts behind several autopilot techniques. The second part is practical, where I will demonstrate an example of a poorly performing flight controller and explain why having an ineffective flight controller can be problematic. So, let's start with the theory. But before diving into control approaches, I want to address a common question that confused me when I first began researching this topic. While reading the literature, I often came across two different terms: autopilot and flight controller. So the question is, are flight controller and autopilot the same, or there is any difference? The truth is that there is no official distinction between these terms. Autopilot is typically used in industrial context, while flight controller is more common in academical and educational areas. For this video, I will define them as follows. Autopilot is a system that allows drones to operate autonomously. It means without any help from the human side, either by navigating from waypoint to waypoint or performing complex missions with decision-making algorithms. A flight controller, on the other hand, is a device responsible for drone stability, control of it, and sensor integration. It processes sensor data to maintain control over the drone. With these definitions in mind, let's explore three common types of autopilot systems used to control the drones. The first type is the PID controller, which is one of the most fundamental and widely known control techniques. To describe the functionality of a PID controller, it makes sense to describe each component separately. The first component is the proportional part, which computes the difference between the process variable and the set point. The most important parameter is the proportional gain, which generates a so-called proportional response. For example, if the magnitude of the error between the real value and the desired value, or set point, is 20 and proportional gain is 3, then the proportional response is 60. Pretty simple math, right? It's important to find a trade-off in proportional gain, because if it's too small, then the whole system reacts slowly when compensating for this error. Conversely, if the value of the proportional gain is too high, the system will start to oscillate, which indicates that the control system is unstable. The second component of PID controller is the integral part, which sums up the error over time. Its main purpose is to bring the so-called steady-state error to zero. However, a significant issue with the integral part is the integral wind-up phenomenon. This occurs when the set point changes rapidly, causing the integral part to accumulate a significant error during the rise period. This effect is a major problem, and there is anti-wind-up techniques available which are not relevant now, but can be explored further if you're interested. The last component of PID controller is the derivative part, which adjusts the output based on the rate of change of the error between the real and desired values. It's an important part that improves the system stability by damping oscillations. But in practice, the D part of the controller is often not used, because in many cases a PI controller is sufficient. The adjustable parameter for derivative part is the derivative time. The larger is the derivative time, the stronger and faster system reacts to changes in the error term. In an ideal case, where there is no noise, it's useful to use a large derivative time. However, unfortunately in reality, there always exists some noise. Because of this problem, we need to balance the value of this parameter. because if it's too high and the sensor response is noisy, or control loop rate is too slow, then the system can become unstable. As you have seen, there are several parameters that need to be adjusted. The adjustment process called tuning. Of course, you can tune these parameters randomly, but it will take a lot of time to find the optimal solution. A much better and smarter idea is to use specific tuning techniques. There are many tuning techniques available, but the most popular and simplest one is the Ziegler-Nichols method. The second autopilot technology, which we will explore, is called fuzzy logic control, or in short just FLC. Unlike traditional control methods like PID, FLC does not rely on an explicit mathematical model of the system. Instead, it uses a set of rules based on expert knowledge and intuition to determine the control actions. This makes it particularly effective for handling uncertainties, nonlinearities, and imprecise system dynamics, which are common in UAV systems. But how does it actually work? What are the steps involved in this control technique? FLC operates by simulating human reasoning in decision making. It uses fuzzy logic to translate linguistic rules such as if drone is moving too fast, reduce thrust, into actionable command. The process is broken down into the following steps. The first step is fuzzification. In this step, crisp inputs like error in position or velocity are converted into fuzzy variables using the predefined membership functions. These variables are represented as linguistic terms such as negative large, 0, or positive small. After fuzzification comes the next step, which is inference. It applies a set of if-then rules often created by domain experts. For example, if the error is large and positive, then increase trust significantly. Or if the error is small and negative, then slightly reduce trust. The last step of this method is so-called defuzzification. This transforms the fuzzy outputs back into crisp values, using techniques like centroids methods, for example. These crisp values serve as control command sent to the quadcopter. This technique is often used as add-on to other control mechanisms, especially in the outer control loop to manage position and trajectory training, while the inner loop handles attitude stabilization. For example, in the study of low-cost quadcopter, FLC was employed to adaptively adjust PD controller gains to improve trajectory tracking performance. This is known as self-tuning fuzzy PD controller. In this research, FLC adjusts proportional and derivative gains based on real-time system behavior, ensuring better handling of disturbances and modeling accuracies. This process is called adaptive gain tuning. Fuzzy logic controllers have many benefits. Firstly, FLC can be implemented without requiring a precise mathematical model of the system, making it suitable for complex and uncertain environments. Additionally, the rule-based structure enables FLC to adapt the changes in system dynamics or external disturbances effectively, which is a sign of its robustness. One more advantage of this method is intuitiveness. Rules and membership functions can be created based on operator expertise, making it accessible to non-experts. On the other hand, designing the rules can be challenging. Creating and tuning fuzzy rules and membership functions can be time-consuming and may require iterative refinement. Furthermore, For systems with many inputs and outputs, the computational complexity can increase significantly. Without proper tuning, FLC might underperform compared to model-based controllers in some scenarios. So, the last technique which we will explore in this video is based on neural networks. Unlike PID controller, which use simple mathematical models, neural network controllers are inspired by how the human brain works. They are particularly effective for managing complex, nonlinear, and uncertain systems. Neural network controllers consist of an input layer, hidden layers, and an output layer. The network learns by adjusting weights through training algorithms such as backpropagation, for example, which allows it to adapt to system changes in real time. For drone control, neural network-based controllers work through several key processes. First, during online training, the neural network learns in real time by observing system behavior and adapting to disturbances. For instance, it can adjust for unexpected wind gusts. Next, the neural network compensates for disturbances such as turbulence by analyzing drone dynamics. Finally, it continuously refines weight parameter to optimize system response, providing smoother and more precise control with minimal error. Neural network controllers are highly adaptable and accurate, but require significant computational power. Proper weight initialization is crucial to avoid instability during training. In practice, they can be used alongside traditional methods like PID controllers to combine robustness with adaptability. So, these are just some of techniques used for drone control. There are other advanced methods such as sliding mode control or H-infinity control, but they are beyond the scope of this video. Of course, if you are interested, I will include links to relevant papers in the video description. Now, let's get started with the practical part. As I mentioned before, we will use in practical part the AirSim simulator developed by Microsoft and PX4 open source autopilot system. So, now I will present you the practical part of this video. And for the practical part, I have wrote the short Python script, which is just 137 lines of code. And this code simulates the drone behavior for the agriculture purposes. So the main goal of the drone is to distribute the chemicals over the field. And overall, for the practical part, we need just three components. Firstly, we need the source code, which is here. We need a flight controller, which is installed on VSL. VSL stands for Windows Subsystem for Linux. We need that because PX4 is robust for Ubuntu systems, and that's why VSL is a good solution, because we don't need to use any virtual machine or like toolboot system. We can just simply install the VSL and use the PX4 flight controller from there. Now we will start the CTL version of the PX4. CTL stands for Software in the Loop, and Software in the Loop is a good thing because it allows to use the flight controller without any hardware. So it's basically just a simulation in a software. So if we will press an enter, then PX4 flight controller is started, the connection is built here, and we see that we are ready to operate the drone and the flight controller. And the last part which we need is our simulation. So this is our drone.
and this is our working space. Actually, it should be like the real agricultural field, but in this case, I just use the approximation. I use the baseball field, which is a good approximation of the real field with vegetation, because it's also like to the plane, and here we can see all of the work. So, to start the simulation, uh, like simulation of the drone work, I already started the Unreal Engine simulation. I have started the flight controller, and I'm ready to start the code here. Um, so I start the code, and now we switch to the simulation, and we see that the drone takes off, and it will start to fly. It will plot the trajectory in real time. I will for now just close it and explain you at the end why it's not that good to have a bad flight controller. We already can see that the drone not flies the direct lines which it should actually fly, which was the plan. It flies like some, I would say, curves with this like rotation and like tumbling. But overall, it looks not that bad, right? So the flight controller uh, basically makes a good work because the main purpose, the main trajectory is followed by the drone, but just the lines are not straight, and also we can see that the landing point is kinda not equal to our start point. And now let's see the path which it flies. And it looks terrible, right? So in principle, it looks correct. Why it looks correct? Why the main idea is that the uh, drone flies so-called dubbing curves, which are the optimal representation for 2D trajectory planning, and it consists on the lines and the arcs between those lines. But of course, the lines need to be straight because it distributes the chemicals, and with such deviations, we can see that, for example, this piece of the field receive more than needed chemicals, and for example, this part of the field is not that good to proceed with their chemicals. And this is issue with the flight controller, and as you can see, flight controller can do its work, but the result can be not sufficient because or not satisfying because yeah, there are some problems in the flight controller and yeah, position control. That's why we need a good autopilot system or like flight controller system, because with the good algorithm, with the good flight controller, we will obtain our result as expected, 100% amazing. Now it looks not that good. That's everything what I want to say uh, in the practical part, and it's a good point to finish a video. So there, ladies and gentlemen, thank you for your time and thank you for attention. I hope you have enjoyed this video, and see you next time. Bye bye.